Okay, everybody. Today in robotics, we're going to be looking at observing mechanisms, which is again our major unit. And the subunit we're going to be talking about is gear trains and motion. You've probably heard of motion before, but gear trains might be something new to you. Don't worry, it's not a choo-choo train. First of all, just like always, we're going to look at our essential questions. Again, not going to be in your notes. Things I want you to understand that you're supposed to be looking for and learning during this lesson, and the conclusion questions will probably talk about those things. Okay, first of all, what is the effect of having a large and small gear when they're connected? So if I have one large gear and one small gear, depending on which one's the input and which one's the output, we're going to have different effects. Secondly, how do you determine the gear ratio of a system of gears? What that means is if I turn my input gear with my hand crank, if I turn it 4 times, how do I figure out how many times the other gear is going to turn? And what are the different types of motion and how do they differ? Meaning we've got 4 different types of motion we're going to talk about. How do we tell the difference between each one? And then how eventually do we look at things in the real world? So first of all, we're going to look at a definition. When gears are interlocking teeth like this, like you can see in the picture, they are called being meshed. And off to the right on your notes, as you can see, this is the first thing that you're going to enter into your notes, that term meshed. So when we talk about gears being meshed, I want you to understand what that means. Second thing we're going to talk about are gear trains. Okay, and we're going into this pretty quick. So now that we know the definition of meshing 2 gears together, what a gear train is 2 gears that are meshed or more. So 2 could be 3, could be 4. As many gears as you want to connect end to end, those gears are now meshed when the teeth are interlocking. If they're not meshed, they really don't do anything, they just spin. So here's an example of 2 interlocking gears. This one actually has 4. The 3 inside plus the 1 big outside gear. And obviously this one has many gears going on, and different kinds of gears we're going to talk about later as well. I think this one might just be CGI, but it does show a good example of how you can have a lot of gears all meshed together. Basically what we use a gear train for is to either well, there's several things, but mainly what they're used for is to either increase and decrease speed or increase or decrease torque. You can also just get motion further away than when you started. So if you can have a gear, all the way on one side of the room, and you could have gears connecting all the way to the other side, you could accomplish tasks far away from where you started. But mainly when you create gear trains, which is meshing 2 gears together, you're trying to increase the speed or increase the torque. In addition to this, they have what we call an inverse reaction, meaning if you increase speed, torque has to go down. If you increase torque, speed has to go down. And that just has to do with the conservation of energy that you're putting into the machine. So when you crank it with your hand, it can't be more force and increase speed. It just doesn't make sense. You're not giving it enough force for that to happen. First thing we're going to do is we're going to look at this table. As you can see, this is already filled out in your notes for you. So what we're going to look at is, if I get that given combination, do I increase the speed or decrease the speed, or does it stay the same? Do I increase torque, decrease torque, or stay the same? Remember, on the left side we have our input drive, okay, meaning that's my gear that goes in, that's where I'm cranking, that's where my hand crank would be, that's the gear that I'm turning with my own hands. On the right side we have the output, what we call the driven. That's the one that gets affected by our gear. So the question is, if the gears stay the same size, what happens? Well, the idea here is it actually stays the same. So when I crank the gear on the left, the gear on the right turns the exact same amount. And it makes sense. They have the same number of teeth. They interlock. As one turns a full revolution, the one on the other side will turn a full revolution. Well, since speed stayed the same, torque also has to stay the same. It's a balance. Okay, when one goes up, the other will automatically have to go down for that to make sense. On the right side, as you can see, there's a spot for you to write this into your notes, and we're going to continue this as the pages go on. Okay, the next one we're going to talk about is when you have an input, on the left side again is our input, that is a small gear and you're going to a larger gear. So what you can think about here is every time I turn that little gear, it's going to turn the big gear as well. But in order for that big gear to turn a full way around, every single one of those little teeth has to get turned through. So in order for that to happen, because there's so many less on the left side, it's going to take more turns of the small gear to make that big gear turn. What does that mean? It means that my speed's going down. It takes more turns, so I could be spinning that thing 3 times as fast, and the wheel on the right will only turn 1 time in that amount of time, so it's going to definitely be slower. Because the speed is decreased, that means the torque is being increased. So when you want to increase torque in your system, you go from a small gear and you're in the input, and on the output or the driven gear, it is a larger gear. Doesn't have to be the largest gear, but anything larger will increase torque. The last combination is to start with a large gear and go to a small gear. So again, I'm going to be cranking the one on the left side, and every time I crank that 1 time, the one on the right side is going to turn several times. So for 1 rotation on the left, I'm creating multiple rotations on the right, which is of course mean I'm increasing the speed. Because the speed is increasing, the torque has to be decreasing. So that's going to be decreased. Okay, what we're going to talk about real briefly is an example that uses these. So bikes have different kinds of gears. When you ride uphill, your wheels are difficult to turn, so you're having a hard time pedal. So you actually want to use a gear that gives you more torque. And I'm not a bike expert, so I can't tell you if it's first gear or 10th gear, but you would use a gear combination that creates more torque. If you look near the back of the bike, on any bike that has multiple gears, you'll see as you switch gears, you go to larger and larger rings, basically larger and larger gears. So you're creating more of an equal balanced pedal, okay, which is constant size. You're basically taking, as you go through the gears, you're creating a gear system that is almost closer to your pedal gear, which is right, if you look at the picture of the bike, it's that circular area where the pedals are. When, on the other hand, you are going on a flat piece of land, or even downhill, this is an opportunity for you to get more speed. You do not need a lot of torque. It's easy to pedal the wheels. So what you do is you use a gear that gives you more speed because you can go faster. So now we're going to do an example on our notes here. This picture is in there. First of all, I would like to know which gear train would give you more torque. And secondly, which gear train would give you more speed? So is A going to create more torque or more speed, or is B going to create more torque or more speed? So as you know, these notes are off to the right side. So make sure that this is added into your notes. Pause it while you make that decision, and then hit play. And this is again just to check if you understand the big gear to small gear. Notice where the pedals are. Okay, so looking at A up there, we start off with a much larger gear and we go to a much smaller gear, which means we're going to be increasing our speed. So that is going to be the bottom one. On the right side, we're starting at a small gear, which is our pedal, and we're going to a larger gear. So that's going to help us create torque. So B, since it's small to large gear, and A, since it's large to small gear. And I really do think you should add that into the notes if possible, because we want to make sure we remember later how this is helping us out. So moving on to the next thing, so hopefully now you've gained an understanding of how just basic gear rules. Large gear to small gear goes faster. Small gear to large gear, more power. Pretty basic. Suppose you wanted to know how much faster one wheel spins compared to the other. So we call that a gear ratio. So in addition to that, we're going to talk about the number of teeth and the diameter. These are 2 different ways to determine the gear ratios between one gear and another. My thing with it is diameter is tough. You're going to have to get out the caliper. You're going to have to make precise measurements. If you know the number of teeth, this becomes very, very simple, because every one tooth that turns, one tooth turns on the other one. It's very simple. They will not skip teeth on these gears. They're very nice quality. So the good news is there is a simple equation for this. The equation goes like this. You take the number of teeth on the output gear, the driven gear, second gear, and that goes on top. You take the number of teeth that go on the input gear, and that goes on the bottom. Okay, you turn that into a fraction and you simplify. It's pretty simple. The second choice is to take the diameter of the output gear, so the second gear, the driven gear, and take the diameter of the input gear. Like I said before, this works if you're running into difficulty, but remember that it's much easier to use the number of teeth on a gear if you can. So let's look at an example. Suppose the drive gear has 80 teeth and the driven gear has 20 teeth. Okay, so something like this. The left one is the one I'm turning, the right one is the one that gets turned. Now we know that the right one is going to turn faster than the left one. Okay, so we're expecting that maybe the driven will turn, 10 times for every 1 time that the other one turns. Well, what you're going to see is it's a very simple equation. We start off with output on top, which is 20. And then we have the input on the bottom, which is 80. Again, this is a review in simplifying fractions. We look for the largest number that divides into everything, which is 20. But you could just cut it in half. 10 over 40, 5 over 20, then 1 over 4. So no matter what you do, you'll eventually get yourself simplified to the correct fraction, which is 1 over 4. Now I can tell you part of the thing that confused me about these gear ratios is I then wanted to say that outside turns 1 for every inside turns 4, and it's not quite the way it works. What you have to look at is what you have to do when you look at this is you have to say, okay, so if input's turning 1 time, the output is going to turn more times. So what this is telling you really is that the driven gear is turning 4 times for every 1 time of the drive gear, which I understand is a flip-flop of the way the equation works. So what we're going to do is we're going to fill out this table together. As you guys can see in your notes, we have the first one done. So what you're going to do is you're going to practice writing the gear ratio and simplifying it. So here I would have 40 over 8, okay, because 40 is the output gear on top, 8 is the input gear on the bottom, and I then simplify that to 5 over 1. So that's the first step you're going to do, and you can see you're going to do this for the rest of the problems. Then you're going to write an explanation. For this particular problem, what it's saying is, it's saying the input turns 5 times, and the output turns 1 time. So the input is always the top of the gear ratio, how many times that will turn, and the bottom is always the output gear, how many times that will turn. So try to set up and simplify these equations. If you get stuck and can't write your explanation, we can do that together, but try to do as much of it as you can. Pause the video and make sure that you remember that it is in fact on your notes, and the table looks just like this. Okay, so we're going to go ahead and get started here. Remember that what you're going to use is the output is going to be going on the top, and the input is going to be going on the bottom. Okay, after you have that, you're going to want to simplify it. So remembering that the way we simplify things is divide into the top and bottom. So I know that 9 divides into that and leaves a 1, and 9 divides into that and leaves a 4. So that has left me with 1/4. Now remember, the simple way to look at it is input on top, output on the bottom now. So for every 1 time the input turns, the output will turn 4 times. And that's coming straight from the equation. Okay, next problem. This time 48 will be on top, and 6 will be on the bottom. The reason is output on top, input on bottom, and then you pretty much flip-flop it when you go to read it in words. So that will simplify out to 8 over 1, which means the input turns 8 times for every 1 time the output turns. Which makes sense. We're starting with a small gear. We're going to have to turn it a bunch of times to make that large gear turn. Okay, the last one might be a bit confusing to you guys. What you end up with here is you end up with 20 over 16. But unfortunately, that one doesn't simplify out neatly. So what you have to do is you have to look for numbers that will go into both 20 and 16. The first one I thought of was 4. And that leaves you with 5/4. Since 5 is prime, you know you're done. And from there, you can go ahead and say, all right, the input turns 5 times, the output turns 4 times. Okay, the last part of the thing we're going to talk about today is the 4 different types of motion. Okay, there are 4 different kinds. First off, we're going to talk about rotary motion. That means it turns in a circle, something that rotates around in a full circle and continues to rotate, either clockwise or counterclockwise. Oscillating is back and forth in an arc. So it's almost like half of a circle, but it actually goes back and forth across that half of an arc. Linear is a straight line in just one direction. You're not going to find too many linear types of mechanisms. Usually they're reciprocating, because what reciprocating means is it basically goes back and forth in a straight line. So it does go out, but it's going to come back again, and back and forth and back and forth. There are some products we've designed as people that actually do all 4 types of these. Okay, the last activity for the day, what I would like you to do is I would like you to take a moment and kind of go through all 6 of these different products. And in that, I want you to do 2 things. I want you to label the input, meaning if looking at this thing you decided, okay, that's the input right there. On your paper, you would label that input. You don't have to put arrows like I did, but you do need to write the word input. Same thing for the output. Write the word output on your paper, wherever you believe the output would be. In addition to that, off to the side, as you can see, I want you to identify the type of motion that occurs on the input and the type of motion that occurs on the output. Mainly, we're trying to pay attention to, does it change? Are we turning rotation into linear? Are we turning oscillating into, and then we could start examining the mechanisms. So this is going to be something that we discuss as a class. They're already all on your paper. So take your time, really think about it, and try to determine the input and output. There may be even more than one going on the devices shown on the screen. Thanks for watching.